Hello, everyone. Next we will learn about the variable frequency drive, VFD. This is a Mitsubishi VFD. We can clearly see the actual wiring configuration of the VFD. The wiring of the VFD can be divided into three main sections. The ground wire, the main circuit, including 6 terminals, and the control circuit, including 6 signal wires. The first step is to connect the ground wire. Next, the main power is supplied to the VFD through L41, L42, and L43. These 3 wires provide the VFD with the high power supply. The output from the VFD is a 3-phase output, U, V, and W. Be careful not to reverse the connection order, otherwise the motor may rotate in the wrong direction. U, V, and W are thick wires, as they carry the high power output. These 6 wires share the high power supply. Next are these 5 signal wires plus a 0 volts wire. First, we look at 3 wires, 0.5, 0.6, and 1.0. 0.5 connects to DRL, which is the low-speed signal of the motor. 0.6 connects to RL, which is the medium-speed signal. 1.0 is the stop signal of the motor and connects to the 5th terminal MRS. After connecting these 3, check 0.4, the forward rotation signal of the motor, and connect it to STF, the 4th terminal from the bottom. 1.6 is for reverse rotation and connects to STR, providing the reverse rotation signal to the motor. And finally, the 0 volts wire, which is the return signal of the motor, connects to SD. With this, the VFD wiring is completed. Let's review. The first section is the ground, the second section is the main circuit, and the third section is the control circuit. After completing the wiring, we need to carry out an inspection. Once the VFD wiring is finished, the power can be turned on. After powering on, we can adjust the frequency or operation mode of the VFD by rotating the knob. Once the wiring is completed and the cover is restored, this concludes the entire wiring process of the VFD. Alright, next we will learn about the wiring procedure of the servo driver. The servo driver is divided into several sections. The first section is the high power section, with the left part serving as a counterpart for comparison. From top to bottom, they are L and N, where 220 volts are supplied. Then 2 resistors are connected here. Below the resistors, for wires, U, V, W, and ground are connected. These supply power to the servo motor. Looking back at the right side, there is a terminal block used to connect the CNE signal wires, corresponding to the plug on the left side. In actual use, only 4 terminals are connected. 2 power and signal wires from the PLC control the servo driver's direction and pulse. Below that, we can see CN2, a terminal block connected to the stepper motor's encoder with 9 wires. This is the overall overview. Next, let's proceed with the wiring work step by step. From top to bottom, the first wire connects to L live, and the second wire connects to N neutral. This is the incoming power supply from the transformer, and T is left unconnected. Below that, P and PC are connected to 2 series resistors, with P connected to R1 and PC connected to R2. Further down, the wires corresponding to U, V, and W are connected to W2, V2, and U2 respectively. Ensure that all wiring is secure, and that connections between terminals and screws are tight, to avoid poor contact due to human handling. Next, connect these signal wires. Inside the connector, multiple terminals are included, but in actual use only 4 are utilized. Connect them smoothly and tighten the screws to secure them. This serves as the servo driver's control signal interface, coming from the PLC. Below that are 9 wires from the encoder, which should also be connected and secured. Finally, check both sides to ensure all connections are correct. This completes the wiring procedure for the servo driver. Now let's look at the position. This is the servo driver. In this equipment, a MareSci Technology servo driver is used. The servo driver circuit is divided into 2 sections. The upper section is for 2 signal wires, and the lower section is the high power drive wires. Next, we will go through them one by one. The 2 wires on top are pulse wires. The first wire connects to Q0.3 from the PLC. The second wire connects to 0 volts, from which 0 volts current flows out. Other interfaces below are configured via software, and will not be detailed here. The second section contains 6 wires. The top 2 are the input wires for the PLC stepper motor. The second wire, V positive, comes from 24 volts. The GND wire carries current, which then splits into I positive, I negative, B positive, and B negative. The 4 wires, I positive, I negative, B positive, B negative, are the ones actually connected to the stepper motor, enabling it to be driven. This completes the stepper motor wiring. Additionally, the stepper motor requires dial and code adjustment. Counting from bottom to top, positions 1, 2, 3, and 4 are the current selection switches, and the following switches are for microstep selection. Under normal circumstances, the specific operation is as follows. Set switch 3 to on, skip 4, and then set 5 and 6 to on. Once these are configured, the motor can be adjusted to rotate 1 full turn according to the preset value, with the required number of pulses. This completes the practical operation of the stepper motor and covers all wiring-related content. Now let's study the low-voltage power circuit. The so-called low-voltage section mainly comes from the PLC and similar devices, where the current is only a 5 volts electrical signal. In this lesson, we focus on the PLC. Please refer to the section. This is the PLC input module, which has 11 interfaces for collecting sensor signals. These sensor signals are converted into 5-volt signals and acquired by the PLC. These 11 sensors can be divided into 3 main categories. First category, proximity switches. Among these sensors, there are 2 types of proximity switches, those for the stepper motor and those for the AC motor. The proximity switches use 3-wire connections, also called 3-wire type 1 24 volts wire, 1 0 volts wire, and 1 signal wire. The wiring corresponds as follows. Blue wire is 0 volts, brown wire is 24 volts, and black wire is the signal wire, connecting to B2, B4, B6, etc. Another type includes 6 blue proximity switches for the X and Y axis. X-axis origin, X-axis left limit, X-axis right limit, Y-axis origin, Y-axis left limit, and Y-axis right limit. They are also connected here in the same manner. Second category, photoelectric switches. The photoelectric switches referred to here are material detection sensors, such as IGN sensors that detect the presence of materials. These are connected to this point and transmit signals to the PLC. Third category, cylinder position sensors. These are used to detect pneumatic cylinders and determine whether material is present. They use a 2-wire connection, corresponding to B10 and B11. Blue wire is 0 volts, and the middle wire is the signal wire. Only these 2 wires are required. These 11 sensors collect signals from the mechanical system and transmit them to the PLC. The PLC runs the program and executes subsequent actions. This is the operating principle of the 11 sensors. The 3-wire signals from B1 to B10 are transferred to this position on the left equipment, which we call terminal block 2. On terminal block 2, we find positions 16, 17, 18, 19, 20, 21, 22, 23, and 27, 28, 29, totaling 11 points. These correspond to the signals collected by X8, which are mapped to I0.7 to I0, I1.7, and I2.5, I2.6. These 11 signals are transmitted to the PLC. In other words, starting from the sensors are first connected, then the signals pass through this wiring, go through the terminal block, and are finally transmitted to the PLC, providing the PLC with the collected signals. This forms the first part of the low-voltage circuit, the signals from 11 sensors. The signals from these 11 sensors are transmitted via wiring and terminal blocks to the PLC. This completes the first part of the low-voltage circuit. Next, we will study the second part of the low-voltage power supply, which is the control panel. The control panel in this area manages the low-voltage control of the entire mechanical system. This panel has a total of 9 switches. Different operations generate different signals, which can be divided into 2 groups. According to the panel layout, the first group includes start, stop, origin, 2D platform control mode, and manual mode. These generate or input signals that are transmitted to the PLC. The second group, separately outlined, includes X-axis positive and X-axis negative, which generate signals to the PLC when their buttons are pressed, and similarly Y-axis positive and Y-axis negative. These 9 buttons provide control signals to the PLC, enabling it to control the operation of the entire system. Next, we explain the function of each button. First, let's look at the 2D platform control mode button. When set to the manual position, the system operates in manual mode, and X-axis positive and negative can be adjusted manually. When set to the automatic position, the system runs according to the PLC program, while manual operation is disabled. This is the function of this button. Next, let's look at the knob below, manual adjustment mode. In this mode, when the knob is set to manual and switched on, the clutch engages. When engaged, the device's automatic operation mode is disabled, allowing manual punching operations. When the origin button is pressed while the system is in automatic mode, the equipment returns to its origin. Pressing stop in automatic mode stops the system commands, and pressing start in automatic mode initiates system operation commands. This concludes the detailed explanation of the button functions. How are these buttons wired? The incoming current generates a 0-volt signal, which flows through the system and passes through terminal block 2. Through multiple interfaces on this terminal block, the signals are transmitted to the PLC. The 9 wires from the panel are connected to the PLC, providing it with control signals. This completes the second part of the low-voltage power supply, the control panel. Next, we move on to the third part of the low-voltage system, the PLC output signals. The output signals, ranging from Q0.0 to Q1.6, include more than 10 signals. The first group of signals generates control commands to drive various motors, VFDs, servo motors, and stepper motors. The first part of the signals controls 2 servo motors via Q0.0, Q0.1, Q0.2, and Q0.7. Among them, Q0.0 and Q0.2 control the X-axis servo motor. Q0.0 is the pulse signal for the X-axis, and Q0.2 is the direction signal. Q0.1 and Q0.7 control the Y-axis servo motor. Q0.1 is the direction signal, and Q0.7 is the pulse signal. Signal Q0.3 controls the pulse signal for the stepper motor, connected to the equipment at this position. Now, regarding the AC motor, as we discussed earlier, only 5 control signals are needed, plus a neutral wire. They are Q0.4, Q0.5, Q0.6, Q1.0, and Q1.6. Among them, 0.4 is the forward rotation signal for the AC motor. 0.5 is the low-speed rotation signal. 0.6 is the medium-speed rotation signal. 1.0 is the stop signal. And finally, 1.6 is the reverse rotation signal. These 5 signals are connected here to control the movement of the AC motor. 2 are used here, 2 here, and 1 here, totaling 5 wires. Finally, let's review. These 2 wires plus 2 and 1, together with the other 5 wires here, make a total of 10 wires used to transmit control signals, thereby controlling the motor operation from the PLC output. This completes the third part of the low-voltage system. We now continue with the fourth part of the low-voltage power supply. As mentioned, the PLC outputs 15 signals. 10 of these control the motors, and the remaining 5 signals are Q1.1, Q1.2, Q1.3, Q1.4, and Q1.5. Q1.1 controls the battery clutch, Q1.2 controls the battery brake, Q1.3 fixes the battery clamp point, Q1.4 controls the positioning electromagnet, and Q1.5 controls the origin electromagnet. Since this involves electromagnets, a larger current is required, but the PLC output is only 5 volts, which is insufficient. At this point, intermediate relays are needed. The signals from Q1.1 to Q1.5 act as input coils. When energized, the relays close, producing a 24-volt signal. This 24 volts power supply drives the corresponding coils, allowing them to engage. The output signals Q1.1 to Q1.5 are wired to the 4th, 5th, 6th, 7th, and 8th positions on the intermediate relay. The main 24 volts wire comes into the relay, and the outputs YE1, YE2, YE3, YE4, and YE5 are connected to the respective coils. We use a multimeter for testing. First, connect 1.1 to the 4th intermediate relay. The multimeter beeps, indicating normal operation. Then connect 1.2 to the 5th intermediate relay, which also functions normally. This verifies that the generated YE1, YE2, YE3, YE4, and YE5 signals are properly supplied to the corresponding coils. YE1 controls the battery clutch, and YE4 controls the battery brake. This means that when AC power comes in, it passes through the shaft inside the large gear and then through a clutch. When linkage is required, the clutch engages, allowing the punching mechanism to move up and down. When linkage is not needed, the clutch disengages, but the shaft still has inertia and continues to rotate. At this time, a battery automatically brakes the shaft. This concludes the explanation of YE1 and YE4. Now, looking at this position, it is a fixed clamp electromagnet. Suppose a piece of material, for example, several sheets of paper, is placed here. When powered, it clamps the material for positioning, allowing punching to proceed. This is the positioning clamp electromagnet, YE3, generated by YE1. Here, this is the origin electromagnet. The equipment has only one origin position. Its coil engages to move the origin upwards. The one generated by YE4 is called the solenoid valve positioning electromagnet, used to control pneumatic signals. When powered, the solenoid valve is energized, the pneumatic system extends, and the worktable film is locked in place for punching. Punching can then proceed without movement. This is controlled by YE4. Without power, YE4 is not energized. The pneumatic system cannot operate, and the spring automatically resets the solenoid valve positioning electromagnet. Finally, to summarize, this equipment requires 5 24 volts intermediate relays. YE1, YE2, battery brake and battery clutch. YE3, fixed clamp electromagnet. YE4, solenoid valve control, and YE5, origin electromagnet.